Assalamu alaikum. Good evening, sir. I am going to explain on doing the simulation of the paper that entitled by Analytical Design of Modification of Modified Smith Predictor for Unstable Second Order Process with Time Delay. So this is our folder, and this is the main paper that I'm going to explain it. I send it to you. This is the analytical design of modified Smith predictor for unstable second order process with time delay. We will do the simulation after explaining some benefit of this paper. Okay, and these are our PPT. So first of all, this is an assignment introduced to Dr. Farzad Hashim Zada by Athman Muhammad Hussein Ansari, and this is my student number. And before I'm going to doing the simulation, I am gonna to tell some introduction about Smith Predictor and its modified. Smith Predictor is a method used for closed loop control system to compensate the time delays. As we see here, this is the block diagram of control loops, and this is the functions of it, y of s and u of s, this in Laplace transform. Feedback loops in control systems are always associated with time delays due to the finite speed of sensing, signal processing, computation of the control input, or actuation. Feedback delay is usually considered to be a source of unstable behavior, which should be eliminated from the control loop. So the problem is we should eliminate the unstable behavior in the control loop. An effective way to compensate the stabilizing effect of feedback delays is the application of predictor feedback, such as the Smith predictor or its modification. The main idea of this predictor feedback controller is to estimate the future state of the plant using the predict state in the feedback loop instead of the actual one. The effect of time delay can be compensated. An accurate prediction is able to completely eliminate the delay from the feedback loop. This means that the Smith predictor is able to remove the effect of the time delay on the pulse of the closed loop control and achieves the delayed response of the delay-free plant P of S subjected to controller C of S. So another question it come to us about how Smith predictor works. Its work by uses delay free model of the process to predict the effect of current control action on actual delayed output process, and attempts to remove the effect of the time delay from the closed loop system, and it requires a nominal model of the system and an estimate of the time delay. Stability of the closed loop system is identical to that obtained if the plant's time delay had originally been ignored. So when we add the Smith predictor, this system will be back will be like that by adding the free model of process to compensate for the time delay. This block diagram of the Smith predictor. In the case of perfectly matching internal model, the modified Smith predictor technique is able to stabilize unstable system. While this is not possible for Smith predictor, Smith predictor has disturbance response and the effect of initial conditions. This the robots make the Smith predictor possible for the doing this with perfectly matching internal model. This is the proposed modified Smith predictor in the paper. Many researchers try to design controllers for unstable process with time delay, but it was challenging task. This challenging because the additional phase lag contributed by the time delay tends to destabilize the closed loop system. Tuning rules were proposed by optimizing the regulatory performance under constraint on the robustness and sensitivity to measurement noise. Good nominal as well as robust performance was achieved for stable, integrating, and unstable process with time delays. In order to achieve the desired specification for the given process model, the controllers in the inner and outer loops have to be chosen carefully. Simple control is used for low order process and controller complexity increases for higher order process models. The main drawbacks. The main drawback of the earlier researchers is that they fail to give suitable values of the tuning design parameters. The main drawback of the earlier researchers is that they are fail to give suitable values of the tuning design parameters. The number of controller parameters to be tuned is large. In our work, in the present work on modified Smith predictor using 3 controllers. This is modified Smith predictor using 3 controllers is proposed for second order unstable process models. Direct synthesis. This is the main advantage of this work. Direct synthesis approach is used for controller design because it enables the user to achieve a trade-off between the performance and robustness by adjusting a single design tuning parameter. Suitable values of the tuning parameters are recommended for a class of second order unstable process models after studying their effect on system performance and robustness. This is the main advantage of the proposed work over other recently published manuscripts. Simulation studies will show that the proposed method results in satisfactory performance and improved robustness as compared to the recently reported control scheme. It is observed that proposed scheme is able to work in the noisy environment. So, for this modified Smith predictor, this proposed modified Smith predictor is shown in this figure, where GM naught is the delay free part. These are GM naught is the delay free part of process model, where GM equal GM naught into E exponential to power minus theta s, and the exponential to power minus theta s represent the process time delay, and GP is the actual process which is to be controlled. The two controllers used for reference input tracking and load disturbance rejection are GC1 and GC2. This is GC1 and this is GC2. GC1 and GC2. These are two controllers used for reference input tracking and load disturbance rejection. And GC or GC3, this is uh, the controller stabilizes the delay-free part of the process model, GM not. A low-pass filter, here this is GF, a low-pass filter with the transfer function GF, I think it's equal to 1 by tau fs plus 1, is used to filter the signal y star. Here this is y star, filter the predict signal, this is the predicted signal y star, and we use the filter, low pass filter, to achieve improved robustness. The system and controllers of our proposed is this. This is the equation for GM, and we talked about GM, that free part process model, delay free part process model, and for GF this is low pass filter, and controller GC, GC1 and GC2, and Y by R and Y by D. The symbols R and Y and D represent the set point controlled variable and the load disturbance at the plant input, respectively. R set point, Y control the variable and the load disturbance at the plant input, respectively. And K is the gain. Here we use K is the gain, and T1 and T2 are the time constants, and theta is time delay. It can be observed from the above this equation that Y by R contains GC and GC1, whereas all the three controllers, namely GC, GC1, GC2, are present in Y by D. In Y by D, all these controllers are present here, GC, GC1, GC2, in equation Y by D. GC and GC1 are first tuned to achieve the satisfactory set point tracking, followed by the design of GC2 to get improved load disturbance response. The controller design of GC and GC1 and GC2. For GC and GC1, as I said before, that GC and GC1 are designed to achieve the desired closed loop transfer functions for set point change. The numerator of the desired transfer function is set equal to the numerator of the transfer function obtained under nominal conditions. The order of the denominator polynomial of the desired transfer function is set equal to the number of unknown controller parameters. In the present work, GC and GC1 are respectively assumed as lead lag compensator and PI controller. GC2 is assumed as a PID controller in cascade with a lead lag filter. And for note, we must know a low pass. This is the low pass filter with transfer function GF 1 by tau fs plus 1 is used to filter the predict signal Y star as suggested to achieve improved robustness. In the present work, we are using tau f in the low pass filter equal to theta is considered after conducting various simulation on different types of unstable process. And for simulation study, ideal PID controllers are implemented. This is for simulation study. As I said, ideal PID controllers are implemented by cascading their derivative terms with a low pass filter with a filter time constant equal to 0.01 times. The derivative time constant in the present work, a set point filter with transfer function equal to 1 by t plus s, is recommended to remove the undesirable overshoot in this work. The closed loop performance are compared by applying a unit step change in the set point at t equals 0 and an inverse step load disturbance of magnitude 2 at the plant at t equal 15. Here, So here I'm going to leave the PPT because all these outputs are from the original paper, and I'm going to my special work to do it and see the output there. So for first one, these are our these are our proposed block diagram of modified Smith predictor. It's okay. And here I am saying that in closed loop performance are compared by applying a unit step change in the set point at t equals 0. This is a unit step block with step time 0 and final value 1 with an inverse step load disturbance of magnitude 2 at the input time 15. This is the inverse step load disturbance of magnitude. This is step time after 15. And here the same thing, SPI controller on GC, and here is GC1. This is the filter to get the Y. And if you want, I can put the names directly here. GM note. Okay, down. GM note. It will be clear. Oh, sorry. GMO. And here is the GF. This is GF. Okay. And this is GC1. Okay, now it's okay. Same thing we have. This is GP. Sorry for that, but I forget to write these names there. No, not this one. Control Z. Now just write G and P. Okay. Okay, leave it. No problem. And when we try to run this circuit with the same time that he mentioned in the paper for 30 seconds, and if we go to the output will be these are the system output and control signal. As it results in a large initial change in the control signal. This is the, yes, it's large initial change in the control signal for the assumed change in the set point input. Both the process gain and time delay are increased by 10%, the second one, and each of the time constant is decreased by 5% to check the system robustness. Okay, this is for system output, and this is the control signal, and as you see, large initial change in the control signal for the assumed change in the set point. This for first output. And for the second one, what's the difference here is the proposed strategy gives satisfactory closed loop response under both the nominal and mismatches condition. In this circuit, 10% increase in gain and a delay value and a 5% decrease in time constant. These. So the next step is increasing the gain by 10% and a delay value of a 5% decrease in the time constant. So I'm going to change this time delay and the gain is changed. So I will do another circuit. Sorry, I couldn't make it in one circuit because of time. So here was the different is the time delay is changed from 1.3 to 1.1 to increase that, and the gain is changed, and from here we can see the output. Both the process gain and time delay are increased by 10% and each of the time constant is decreased by 5%. To check the system robustness, the system outputs and control signal under mismatch condition are shown soon. Here this is the our so this is the system output after changing in time delay and gain. This is the process variable and time second for 30 seconds. Here the if we want to see this in the paper, I think this is figure 11. Yes, it's shown in figure 11, system output for this example when GP is not equal to GM. Here he took the output for the proposed paper, and this is the references in 2008 and 2016. I think it's not 2016, and he make a comparative between these. Okay. The system output corresponding to the proposed control scheme in the presence of a random measurement noise. 0 mean and variance equal to 0.01 at the process output. If noise are coming and not 0, here we are suppose that there is no noise here, noise is equal 0, but the next step in the presence of output noise. So I'm doing in another circuit. Here it's number 13. This is with noise. Okay, what's the difference here? Noise is coming, this is noise, or we can write it in by D. This is with variances 0.001, same what he said in the paper. If the noise come, 0 mean and variance equal to 0.001. This is the variance in the noise. Same circuit, but just the noise is different now. And we'll see the output of this when noise are coming. These are the outputs. These are two outputs here. I will explain each one. These are the system outputs of the proposed scheme under measurement noise. These are system output, same as we see before system output, but this is with noise. I think here this is the system output without noise in the paper, and we see it before just a minute, same one, and this is with a noise. Okay, And this is the control signals. Control signals are also affected by noise. It will be different, and it will be more different with the base one. It is observed that the proposed method tracks the reference input signal and rejects the load disturbance, even in noisy environment. It is observed that the proposed method tracks the reference input signal and rejects the load disturbance even in a noisy environment. The high frequency noise is filtered. As we say before, there is a low pass filter. Low pass filter used in cascade. Low pass filter used in cascade with the derivative terms of GC2. This control signal are obtained by setting the derivative filter time constant. This control signal are obtained by setting the derivative filter time constant TF equal to 0.1 TD2 and 0.01 TD2 to get this. This is the control signal for the proposed scheme under measurement noise. Next step is to check the tau effect or GF effect. This is the block of a low pass filter after we change the tau f, and how will be the results. I'll close this one now on this link, and I'm going for last circuit, which is 14. Same circuit, but we remove the noise, but we are going to just to check the effect of changing the GF. You know, this is the GF, low pass filter. This figure shows that when TF equal 0.1 or 0.01 or different, results in much improved control signal as compared to that TF 0.01 in TD2. It is to be noted that these two different values of TF give almost similar system outputs, and to show the effect of GF on the set point tracking and load disturbance rejection response, simulation studies conducted for a range of tau f. In this figure, in this circuit, show the system output. From this figure, we will show the system outputs corresponding to the proposed scheme under the above said mismatches conditions for various 2f. We will change the amount of 2f, and we'll see the effect of tau f on the closed loop response GP naught equal to GM. Here, see the amount here, 0.451. It's 1.5 T. On the second one, 0.3 and 1, and last one, 0.7 theta will be 0.02121. Yeah, if we just run the circuit and bring the related circuit, you will see this. This is the system output after putting the first degree of tau f. Okay, I will take a picture for it. I'm using the sniping tool to get a picture, and I will save it to see the difference between it and the other one. Copy, and I can put it in paint, this first one. Okay. And if I am going to change this, I will close it. This is our circuit. If I am change by delete the first amount and change by second one, and I will run the circuit for 30 seconds same time, and I will bring. Okay, see the difference. I'll put it here, and the last one we did it. It is here. Wow. Oh, sorry. I can't do this, I think. See the difference? There is some difference in the peak. Here the peak 1.4, here 1.5, and the time different. Okay, I will take another picture for this one. Okay, and I'm gonna to close the figure, and going back to the main circuit, I will delete this one, and I will use this last one with 0.7, and oh, sorry, it can't be on. There's something. Okay, now it's okay. This work now. I will run it, and again bring the same output figure, and you will see it is very different with the last one. It's too different. Each time when we change the GF, it's observed from these figures that the varying tau F affects both the disturbance rejection and set point tracking response, but the effect on the latter is less. Yeah, effect on last one is less for load disturbance rejection response. A small value of tau F results in oscillations, and a large value of tau F yields slow response. A small value of tau F results in oscillation, as you see, and a large value of tau F yields a slow response. However, tau F equal to theta gives a smooth and fast closed loop response, and is therefore recommended in the present work. For discussion on the last notes, the proposed modified Smith predictor has three controllers: GC1, GC2, and GC3. In addition, a low-pass filter. This low-pass filter is used to achieve improved robustness in both the works and tuning rules, derived using direct synthesis approach. This is the main advantage by using the direct synthesis approach. However, control structure considered in the literature work is completely different from the proposed control structure. In literature works, they are tried to find this one. Sorry. Literature works, they didn't provide suitable values of the tuning parameters, and also they were failed to give explicit tuning rules for controllers GC1 and GC2. They failed to give robust performance towards small uncertainties in the process parameters. The controllers of the modified Smith predictor are designed using direct Smith synthesis approach. The proposed method involves two tuning parameters whose suitable values are recommended after studying their effect on the closed loop performance and robustness. This is the main advantage of the proposed work over other recently published manuscripts, where the authors provide suitable range of the tuning parameters. Furthermore, the proposed method outperforms the recently reported schemes as they fail to provide robust closed-loop performance for process models having two unstable poles. This simulation example are considered to illustrate the references of the illustrate the usefulness of the proposed work. This is I will close these figures, and here finally you can see this the difference between what we got and what they put in the main paper. And last figure is figure 14, effect of tau f on the closed loop response. He put tau f 1.7 and the theta 1.5 theta. I used the same one, but my figures is separately, each figure alone I took it, and I depend on my references, the base paper and another book, chapter 10. It talks about Smith Predictor and it's modified, and the simulation I did it by using MATLAB 2017B. Thank you for listening, and thank you again, sir. Goodbye.